Okay, well that's good. I now need to get the number of moles because this information is predicated on moles. N, the number of moles, is the sample mass times the molar mass. So that's equal to 44.4 grams times the molar mass of potassium permanganate. What's the molar mass of potassium permanganate?
The answer I found is 157.881 atomic mass units.
Show off. So this is 157.9 grams per mole. Okay? So the number of moles, the number of moles then would be, oh, sorry, that's no, it's sample mass over molar mass. Oh, and this is a good thing because that's a good reason to carry a unit. Because if I had done it this way, without really thinking, I'd have gotten grams squared. And that's not what you want. Your answer needs to be in moles, so you can't have grams squared. That's the value of keeping your units with you. So really, this should be 44.4 grams over 157.9 grams per mole. And that way, the grams cancel out, and the inverse of inverse mole is mole. So 44.4 divided by 157.9, this is 0.281 moles. So coming here, 1 mole of the alcohol needs 0.4 moles of the permanganate. Therefore, number of moles of permanganate is equal to 0.281 times the 0.4, which is equal to 0.113 moles. So that's the number of moles of permanganate that I will need. Wait a minute. Number of moles. Oh, save us. Nope, there's a mistake here. This molar mass is not of the, yeah, this is right. Okay. Apologies. Okay, so the density we're given was the density of the liquid, right, which is the alcohol. And so the density was 0.97, the volume was 45 mils, so it was 44.4 grams of the alcohol. So the number of moles is the 44.4 grams of the alcohol over the molar mass of the alcohol, not of the permanganate. So the alcohol's molar mass, that's C3H8O again, which is 36, that's 36 plus 8 plus 64, no, sorry, plus 16, right? So 36 plus 8 plus 16, so that's 36, 44, 50, 60, so that's 60 grams per mole, so that's what should be here. It should be 60 grams per mole. So that should be a little less than 0.75. So that should be 44.4 divided by 60, which is 0.74 moles. So I have 0.74 moles of the alcohol. If one needs 0.4, then 0.74, 0.74 will need 0.74 times 0.4, which is 0.296. Right. So I actually have my 0.74 moles of the alcohol will need 0.4 of that, 40% of it, which is 0.296. What mass is that? So the mass of permanganate is equal to the sample mass times the molar mass, which is the number of moles times the molar mass, which is 0.296 moles times the molar mass, which was 157.9 grams per mole, which works out to be, so the moles cancel, so it's 0.296 times 157.9, which is 46.7 grams. How many stick picks did I have? So you have 45, so this will be 48 grams. 47 grams. So I'll need 47 grams of potassium permanganate to oxidize 45 mils of the alcohol. Okay. Right, so let me just, because I know I muffed this up, so let me just walk through this again. So we were given the volume of the alcohol and its density. I'm going to convert the volume into the mass. Density is mass over volume. Mass is density times volume. I know the mass of the alcohol. I want to get the number of moles of the alcohol. So the number of moles is the sample mass, 44 grams. 44 grams over the molar mass, which I will work out from the formula. So that's going to be 0.74 moles. I go back to my determination of equivalence of equivalents. One equivalent, 1 mole of this needs 0.4 equivalents of the permanganate. So 0.74 moles will need 0.74 times 0.4, which is 0.296 moles. That's how much permanganate I need. What is that in terms of mass? Well, the mass, right? Mass is number of moles times the molar mass. So it's 0.296 times the molar mass of 158, and that's 47 grams. Okay. One last question. So it's possible to convert, let's say, this compound in the presence of zinc and acid into that compound. So the question is, how many equivalents of zinc do I need to carry out that reaction? And let's just make it a bit more interesting. What mass of zinc, so what mass of zinc is needed to reduce 35 grams of this compound? Okay. Let's find the chemistry first. So I'm going from this compound into that compound. What is happening? Well, I kind of let the cat out of the bag, it's a reduction. But I'm going from a carbon at the alcohol level to one at the alkane level. That is a 2-electron reduction. So this is gaining 2 electrons, right? Because I'm reducing it down one level, alcohol to alkane. In the process, zinc, the only thing that zinc can do in any of its chemistry is to lose 2 electrons. And that becomes zinc 2+. So obviously, one of these needs one of those. And by the way, I can write this reaction as this plus zinc plus 2H plus, well, it's plus H plus, will give rise to my product plus zinc 2 plus Cl minus. And that would be a balanced equation. So I went from this to that, gaining 2 electrons. Zinc went to zinc 2 plus, losing 2 electrons. And that's a balanced equation. There's a 1 plus on this side and a 1 plus on that side. And by the way, there's 1 H here and 1 H here, so that's 2. And then 2 H's here. So we're atom balance as well. If I have 35 grams of the haloalkane, I need to know how many moles that is. So the number of moles of the haloalkane would be the sample mass over the molar mass, which is 35 grams over the molar mass of this compound, and that is C3H367Cl. So that's 36 plus 7 plus 35.5. So that's 6 and 7 is 13 plus 3 is 18. 6 and 6 is 3 and 3 is 6 and 1 is 7. So that's 78.5. So this is 35 grams over 78.5 grams per mole, which works out to be, so that's 35 divided by 35 divided by 78.5, so that's 0.4459 moles. I need 1 equivalent of zinc, because it's a 1-to-1 ratio. So I have 0.4459 moles of the chloride. I need number of moles of zinc would be 0.4459. Right, so it's 1-to-1. The mass of zinc will be equal to the number of moles times the molar mass, which is 0.4459 moles times the molar mass of zinc is 65 grams per mole. So the moles cancel out, and I have times 65, and if I have, so it says 28.98 grams. There are 2 sig figs, so this is 29 grams of zinc. So I need 29 grams of zinc to reduce 35 grams of that haloalkane. Okay, so the forms in which these questions will show up will be this, and they may be as trivial as just how many equivalents do you need, right, which is just the heart of this on the left. They could be more involved where you're given the mass of the substrate of the organic compound and asked for the mass of the reagent, right? And that's a lot of this is Gen Chem stuff. Or you could be given the organic structures and be told and be asked to tell me how many. Is this an oxidation or reduction, and if so, how many electrons? So am I losing 6 electrons? Am I gaining 4 electrons or whatever? And what you want to do is look at the oxidation level of the carbons in the compound and make an assessment. I'll give you one last question on that ilk, just to raise a point. So if I have this compound, and I treat this with aqueous acid, what I get is this compound. So if I ask you, what has happened to that compound? Or I can ask you, is that a redox reaction? So obviously, chemistry is happening here. Okay? What has happened? Well, I'm going from here. So this is at the alcohol level. And this is at the alcohol level. This is at the aldehyde level. And this is at the alkane level. So what happened? In going from alcohol to aldehyde, that's an oxidation. One bond to heteroatom, two bonds to heteroatom. That represents a 2-electron oxidation. But in going from the alcohol level to the alkane level, I have lost one bond to heteroatom. So that represents a 2-electron reduction. So if I asked you what happened to that compound, you can give me one of two answers. From a redox perspective, you can say this is not redox, right? Because I've lost 2 electrons and gained 2 electrons, overall there's no electron transfer. So it's not redox. Or I can say, this carbon underwent a 2-electron reduction at the same time that this carbon underwent a 2-electron oxidation. Now, if you choose to give the latter answer, right, and detail, this carbon underwent a 2-electron reduction, that a 2-electron oxidation, you want to say at the end, therefore at the end, this is not redox. So the ideal answer would be to say, carbon 2 underwent oxidation, 2-electron oxidation, carbon 3 underwent a 2-electron reduction. So overall, because the number of electrons lost, because the number of electrons lost and gained is the same, then overall there is no redox. So to me that would be the ideal answer. So that way you let me know you recognize redox when it happened, you recognize reduction when it happened, oxidation when it happened, you recognize further that the number of electrons lost and gained is the same, in the same molecule, therefore no net redox. Okay, so we'll stop there. The next lecture that I will post is an older one on starting module 2, and I will post that for you today as well. Okie dokie.